Okay, so welcome to the 32nd video in the Discrete Structures series, and we are resuming our discussion of the chapter Induction and Recursion. In the last three videos, we have already finished having a look at induction, and that involved the mathematical induction, the strong induction, as well as the well ordering property. So in this video, we're going to start having a look at recursion, but right off the bat, let me tell you that this is closely related to induction. A recursive definition is also called an inductive definition, and the process of building up from a base case and covering larger cases is the same in the process of induction and recursion. Therefore, we'll start our discussion with a look at recursive definitions, and then we'll be looking at recursively defined functions, and we will also be covering the idea of recursively defined sets. So we'll look at recursively defined functions under two aspects. We'll be looking into a type of problem in which a recursive definition will be given to us, and based on the definition, we need to calculate the value of the function at different instances. And we'll look at another class of problem where we'll be given the problem statement and we'll need to form the recursive definition. And under recursively defined sets, we'll look into an example defined on the subsets of integers. We'll see the recursive definition of strings over an alphabet, the recursive definition for a length of a string, and finally, we'll have a look at recursive concatenation. Alright, so that is the scope. Let's get started with recursive definitions. So a recursive definition is a direct outcome of the process of induction. We should remember how in induction there was a basis step and an inductive step where we needed to guarantee that every given instance guaranteed the next instance. And this core idea is similar in case of a recursive definition also. And before we define what a recursive definition is, let us have a look at this example. I want to consider this sequence of a power of 2's. So I'll start with 1, which is 2 raised to the power 0, and the subsequent terms will be 2, 4, 8 and continued. And we know that for this sequence, any general term is just 2 raised to the power n minus 1. So if I wanted the first term, I would just plug a 1, which would give me 2 raised to the power 0 and this one. Similarly, other values of n produce higher terms in the sequence. So if I form this definition saying any given term a n is given by 2 raised to the power n minus 1, this is a sufficient definition for this sequence. But there is another way to define this sequence, and that is the recursive definition. Here's how that works. So just like the process of induction, it involves having a base step where we know some seed values. So in case of this sequence, I'll start by saying that the first term a1 is equal to 1. And now I can write the following definition. In order to find any term a n, I can take the previous term and simply multiply 2 with it. Therefore, I say that the term an is equal to the previous term an minus 1 times 2. And you should be able to see this is also analogous to the process of induction. We are defining how to find a given term from the previous term. I'll tell you the exact analogy shortly, but for now, let us be convinced that this is the same as this sequence. And I can verify that by starting from my base step. It is given to me that the first term is a 1, so let me start with that. And it has also given to me that any term is the previous term times 2. So if I substitute 2 in order to get 2, this definition tells me that a2 is a1 times 2. And I have established that a1 is 1, therefore a2 is just 1 into 2. And this will be equal to 2, that is my next term. And it should be easy to see that I could use the same relation again to get the third term, and that would be equal to 4. And you could see this is the same sequence as this. So this first way of defining a sequence or anything where I can just use one expression to get value at any instance is called a closed form definition. And this type of definition, which involves a base step and a recursive step, is called a recursive definition. And which type of definition is better? Well, in general, a closed form definition is considered better. Because in a closed form definition, I can directly plug the value of n and get the result that I need. If I want the 100th term, a100 would just be 2 raised to the power 99. But this definition defines a100 in terms of a99. You can see it defines n in terms of n minus 1. And then I have to ask the question again, what is a99? And that will force me to use the same definition recursively, and then I'll get a99 defined in terms of a98. And then I have to follow the definition all the way down until I reach my base case. But that said, some problems are inherently recursive in nature, and a recursive definition will be more intuitive. And lastly, there are a few recursive problems for which a closed form definition does not exist or has not been known yet. So we cannot guarantee that every recursive definition has an equivalent closed form definition, and that is another reason why to study recursion. And I've talked about this in this series a couple of times. There is the collage conjecture, which is a recursive definition. This is also called the 3n plus 1 conjecture, and mathematicians have been studying the nature of the sequences generated by this conjecture for a long time now. A closed form definition for it has not been found yet. And one last thing before we have a look at recursive definitions, it's not the case that it just applies for sequences. We could have recursively defined functions, we could have recursively defined sets, and we could have high-level concepts and structures that are just recursive in nature. For example, trees. So a recursive definition is a way to define a function, set, or structure using the following. So the first one is called base cases or seed cases. Now in terms of sequences, the base case will be the initial few terms. So in general, a base case provides a few seed cases for the function, set, or any other structure that we are defining. And then the second requirement is to define a recursive step. And this is the case where we define a problem in terms of the smaller instances of the same problem. And why do we say this? You could see this definition. An is defined in terms of an-1, but then an-1 also follows a similar sort of definition. So what we have effectively done is reduce the problem to a similar problem of a lower size. And as these problem sizes get smaller and smaller, we are eventually guaranteed to hit the base case. Alright, let's get started by looking at a few formal examples of recursive definitions. And we'll start with recursively defined functions. First, I want to make you aware of a type of problem which is really easy to do. So we'll be given a recursive definition. So first we are given f0 is equals to 3. This is my seed element. And then we are given fn plus 1 is equals to 2 times fn plus 3. And the question simply says find f0 to f4. So we already know the basic. We start from the base case and we keep deriving new terms until we have the number of terms that we need. So this should come really easily. I'll just say f0 is equals to 3 because that is given to me. The next thing that I want is a f1. How do I get f1? By substituting n as 0. You should not be confused. F1 does not mean n is equals to 1. Okay. I want this value to be 1 and I can achieve that by making n 0. So I could write this to be equal to 2f0 plus 3. And I already know what f0 is. That is 3. And I can say this is 2 times 3 plus 3. That is 9. Similarly, I can find the definition of f2. That will just be equal to 2 times f1 plus 3. And you can see that this is just equal to 21. 9 times 2 plus 3. And you can easily complete the order too. It will just be 21 times 3 plus 3 and then one more step after that. So just making you aware, this is really simple, but you want to be able to do this. And before we move on to the next, one important thing, the same recursive definition could be written this way. So this is just saying that the next term is this term multiplied by 2 plus 3. And this is just saying that the current term is the previous term multiplied by 2 plus 3. So these are equivalent definitions. And if this was given to me, in order to figure out f1, I would just plug n is equals to 1. And this part works out itself as 0. So even though these definitions are different, these relationships will come out exactly the same. And for our purposes in this entire chapter, we'll try to prefer this type of definitions where n plus 1 is defined in terms of n. Okay, next we'll look at more important class of recursively defined function problems, and that will involve finding the definitions or forming the recursive definitions. Okay, we already have some idea about 2 to the power n. We'll try to find a recursive definition for a raised to the power n. And the question wants me to consider n from 0. So this is essentially asking me to generate this sequence that starts from a raised to the power 0, a raised to the power 1, a squared, and so on. And we have also established, and this is a rule, in order to find a recursive definition, we want to relate any term with its previous term and find a uniform rule that defines the relationship between every consecutive terms. And let me immediately point out that a definition might not necessarily only involve the previous term. For example, a Fibonacci is the sum of previous two terms. So it would in fact be more accurate to say that a recursive definition defines a term based on previous terms. It's not just the last term but any previous term. It's just like the concept of strong induction. But in this particular example, I can see that any term can just be derived from the previous term by simply multiplying by a. So let us see the pattern. I start from a 1. A raised to the power 0 is just 1. And if I multiply by a 1 times, I get this a. And if I multiply by a again, I get a squared. So I could write my recursive definition with this base case of a raised to the power 0 is equals to 1. And then define a recursive step that every new element can be obtained by multiplying a. So let us do that. We'll just say a raised to the power 0 is equals to 1. And this is my base step. And this can be thought as a function. I could just say this is a function that takes 0 as an input. And let us use the n plus 1 notation like discussed earlier to find the n plus 1 element, which is also equal to a raised to the power n plus 1. And we'll just define this as a raised to the power n times a. And you should change your perspective when looking at a definition like this. It is obvious that a raised to the power n plus 1 is a raised to the power n times a. But the importance of this recursive definition comes from the fact that I can carry out this operation even if I don't know what power is. I do not need to be able to know how to calculate the power of some variable raised to the power of some other variable. Because imagine I need to take 2 cube and I do not know how to take the power 3 of 2. But this definition simply says that this is 2 raised to the power 2 times 2. I still don't know how to take a power, but I can still use the recursive definition. And this is 2 raised to the power 1 times 2 times 2. And I still don't know what power is. But I do know this is equal to 2 raised to the power 0 into 2 by the same definition. And 2 raised to the power 0 being my base step will just be equal to 1. And ultimately 2 raised to the power 3 is just a product of these 4 terms. Okay, so next try this one, n factorial. So we can provide the base case as being 0 factorial is equals to 1 or 1 factorial is equals to 1. Both work. I'll just use 1. And I know that n factorial is just the previous number's factorial times n. So for example, 8 factorial would just be 7 factorial times 8. So I can write my recursive definition. Fn plus 1 is given by n plus 1 factorial, which is equals to n factorial times n plus 1. Okay, let's try a few more. I want to be able to write a recursive definition of sum 0 to n ak. Okay, so this is just adding terms in a series. So I'm adding the terms a0, a1 all the way up to an. All of these are being added. And what is the nature of the recursion here? I can say that the sum is initially just equal to my first value. That is my entire sum. And every time I get a new term, I can just say it's the previous term plus the value of the term in question. And so by the time I reach a2, I already would have calculated a0 plus a1. And I could just proceed recursively until my series is exhausted. So the base case of this situation, f0 would look like the sum from 0 to 0. And this will just be equal to 0. So we are just saying start from 0 and keep adding terms until we reach the sum. So the initial value of the sum is just assumed to be 0. And then we define the recursive step in terms of the next value. Fn plus 1 is the sum from 0 to n plus 1. And how can we define this recursively? We can say it's the previous sum from 0 to n plus the current value. So the term is a of k. And what I want here is the sum from k is equals to 0 to n, a of k. And then I want to add the current term, which is going to be the n plus 1th term. So this should be also easy to see. And in every recursive definition, you want to verify this. I define summation in terms of summation. So the recursive step always defines something in terms of smaller instances of it. So this range from 0 to n plus 1, this only range from 0 to n. That means as you evaluate this recursion, the value of the n is bound to reduce. Ultimately, it will become equal to 0. And that is when we'll apply this base case. Okay, we'll have a look at few recursively defined sets next. So for a recursively defined set, we do two things. Provide the seed elements. And then we provide a rule to find new elements based on existing elements. So let us look at this example. A set of multiples of 3. So I can define this set of multiples of 3 by starting with the base element of 3. So I can imagine a set S and then say that 3 belongs to that set. And the next rule that I'll write and the recursive rule is that if X belongs to S and Y belongs to S, so does their sum. So if I use this definition in order to form this set, I can start with my seed element 3. And then in order to apply this rule, I can just assign X as 3 and Y as 3. See, it nowhere says me that X is not equal to Y. So I can just choose 3 for both. And then that would give me 3 plus 3 is equals to 6. And the claim is 6 also belongs on this set. So 6 is another member. And then I could add 3 again. I get 9. I could add 9 and 6. I get 15. I can also get 12 by adding 6 with itself. So this will eventually cover all the multiples of 3. Okay, we'll see one more example of a recursively defined set. We want to recursively define the set sigma star, which is the set of all strings over an alphabet sigma. So these things will come up in detail in theory of computation. I think that would be in 3rd or 4th semester. But there will be a chapter called language and grammar, and we'll be studying these things in a lot of detail. But for now, let us simply understand this problem as a requirement to generate all strings from 0 and 1. Okay, so this alphabet is given as 0 and 1. And what are all of the strings that I could form from this alphabet? I could form an empty string, which is often denoted by lambda. I can form just a string with a 0 if I want. I can form 2 zeros. 1001 is another example. So basically any string of 0 and 1s, including the empty string, can be formed from these alphabets 0 and 1. And if I collect all of these possible words that can form from this alphabet, I get this set, the sigma star set. And it is defined as the set of all strings over a given alphabet. So how do we start this recursive definition for this set? We want to say lambda or the base element belongs to my set sigma star. So at this time I have enabled my sigma star to contain the empty element. And now what I'll say is that you can take any existing word from this set. You can append a 0 or a 1, whichever you like, and put that new word in. So from the empty string, if I put a 0 at the end, I'm going to be able to get a 0 and a 1, these two strings. And you see from 0, I could get 0, 0 and 0, 1. From 1, I could get 1, 0 and 1, 1. So basically, I could cover and reach any string that I want. So let's capture that idea here. So I want to be able to say if any word W belongs to the alphabet already, and then if I take any of the 0 or 1, so X belongs to sigma, then I can say this would imply that the concatenation WX also belongs to the set of all strings. So this is my basis step and this is my recursive definition. Now let's look at a few common recursive structures to prepare ourselves for our next lecture. So I want to look at this case. Recursive definition for length of a string. So for example, if I have a string called ABCD, its length is 4 because it has 4 characters. So what is the recursive idea here? I'll start by saying that the length of an empty string is 0. We'll just call this lambda. Length of lambda will just be equal to 0. And let me show you the process of how we are going to break this recursively. We're going to say that the length of ABCD is equal to the length of ABC plus 1. So we're going to peel off one last character from this. We're going to add 1 in order to account for its length. And we're going to say it's recursively equal to whatever the length of the remaining thing is. And so this will give me the length of AB plus 1 plus 1. And this will just add up to a 2. And eventually I'll just get the length of A plus 3. And then I'll get the length of lambda, the empty string, plus 4. And I know that the length of lambda is 0. That is my base case. Therefore, I know that the length is 4. So let's form that recursive definition here. So we'll just call this function L for length. And we want to call the length of lambda is equal to 0. Where lambda is the empty string. And then we want to say that the length of any random word. And then we want to divide that word as the remaining word plus its last character. So I want to set this to be equal to the length of W plus 1. So if we want the length of a word like let's say Nepal, we are looking for W as being equal to this phrase and then X being equal to this. And just like we did here, it is going to be equal to the length of this plus 1. Alright, we'll look at one more recursive definition called recursive concatenation. So we'll use the similar idea of splitting the second word. And let me demonstrate that first. Assume I have this string and I want to concatenate this with this string. So it's a really straightforward process. Concatenation just means this first word arrives in full and then this is joined to the end of this one. So the final result would look like abracadabra. And it might be hard to find the recursive nature of this first. But the way we are going to define it recursively is by taking off this last character. So look at this carefully. We want to be able to say that the concatenation of this whole thing with this whole thing is just the concatenation of this whole thing. And everything here except the last character. And the last character will be a part of my result. So it will be clear when I demonstrate with an example. So I want to be able to say that the concatenation of, so this is what I need. And the way I'll achieve this is by mentioning that this is the concatenation of this phrase ABRA and everything in the second phrase except the last character. And then I'll assume that the A is a part of my result. So I'll just put this outside. And you can see using this definition, I defined concatenation in terms of concatenation, but the size of problem has reduced. So I can apply exactly the same definition again and I'll get it is a concatenation of ABRA with CADAB. Okay, and R will be a part of the result. And you can see what will happen eventually. I'll get the concatenation of ABRA. All of this will be exhausted and only the lambda will be left here, the empty string. And then I'll have CADABRA. Okay, and this is going to be my base step. I'm going to say that the concatenation of anything with lambda is just itself. So because the concatenation of abra and lambda is just ABRA and then the rest is just here. So this is how I aim to get my concatenated string at the end. So the base step of my recursive concatenation can take any word and then lambda and then it will produce the same word. So I'll say base step and then I'll say if any word belongs to the alphabet and if I just want to concatenate W and lambda, I'm just going to get W. I used C here in order to show you clearly what was going on. But the concatenation simply uses this symbol, dot. But if I use the dot here, the steps would be hard to distinguish. But formally, we'll just be using the dot notation. So I'm just saying if there's any word in my alphabet, concatenating it with the empty string produces the same word. But what if I want to concatenate this W with some other word? So I'm going to define my recursive step. And I want to write the definition that any word W. And if I concatenate it with any other word, and remember for this second word, I want to consider everything except the last character and the last character separately so that I can take that last character out. So I'm going to represent the second word as W dash X, where X is the last character in the second word and W dash is the rest. And I'm going to define the concatenation in terms of itself. So I'm going to say this is going to be the concatenation of W times W dash and X. So again, this will look obvious and basic, but this captures this essential process. So take the last letter from the second word put it out, and then you get a smaller concatenation. And then I get another letter from W dash out, and that will give me W dash something smaller, and again something smaller. And that will keep continuing until I get the second term to be lambda or empty string. And then I get to use this base case. W times lambda is just W. And that will give me my final string. Okay, so that is the formal discussion of the video. But before I let you guys go, there is something that I cannot go without mentioning you. So this is about the Fibonacci sequence. So you know that a Fibonacci sequence is given by this expression. F0 is equals to 1. F1 is equals to 1. This simply says that the first two terms is 1. And then we know that any term Fn is given in terms of previous two terms. So Fn is just equals to Fn minus 1 plus Fn minus 2. But then in this Fibonacci sequence, for example, if we need to find out something like F20, and this is the same as asking what is the 20th Fibonacci number, we know from this definition that this is equal to F19 plus F18. So in order to find the 20th Fibonacci number, I need to again find what the 19th and 18th number is. So it seems like we'll need to calculate all numbers from 1 to 19 in order to find 20, doesn't it? But fortunately, a Fibonacci sequence does have a closed form formula, and I wanted to show you that formula. Consider this. So earlier in our video, we talked about a closed form expression. So this expression is a closed form expression for a Fibonacci sequence. If I want the fifth Fibonacci number, I can just plug n is equals to 5 in this number, and that will give me the result. And this number 5 is something that you definitely have heard the name of, even if you don't know the value. It's called the golden ratio, and its value is equal to 1.6180. Okay, when I do minus 1 here, I'm just taking the conjugate, so I'm just doing 1 by this value. So you can substitute that here. You can substitute this value for 5, and you can substitute any n and try to figure out if this is giving the right Fibonacci number. And this closed form formula is called Binet's formula in honor of the mathematician. And a quick concluding note, because this formula uses a lot of fractions, you get a lot of rounding errors. So if you need to find the millionth Fibonacci number, it might not land on the exact integer because of landing errors. But this is actually an exact and a closed form formula. And coming back to my point about the nature of definitions, if someone defined Fibonacci sequence using this formula for the first time, I do not think it would have been as intuitive as the recursive definition. Alright, so that's all the discussion for this video. In the next video, we'll be looking into a few more recursive structures and the idea of structural induction. So important topics coming up. I'll see you guys tomorrow with the next one. Have a good day and bye.